This problem will be an example of an integrated rate law. And so just a little saying that when you see a time table, versus concentration, it is time to grab your calculator and make a graph. And so the first thing I'm going to do, I know that I need to graph the time versus two different things, the log of the concentration and then also 1 over the concentration of the reactants that's given. Because I know that log of the concentration versus time, if that is a straight line, which is going to have a negative slope, if that's the straightest line of the data, then I know it's a first order reaction. If I graph and my 1 over the reciprocal of the concentration versus time, if that is a straight line, then I know that I have a second order reaction. In both cases, the slope is going to help me find K. And it's just easier to say that the absolute value of the slope is going to give me my rate constant. So whichever one's the straightest line, I'm going to take its slope, take the absolute value. So if it's negative, it becomes positive. And that will give me my rate constant. So that's what I'm looking for. So determining the rate law, I need to look at the graphs. Then I can integrate it. Once I know which one to write down. You pretty much look on your formula chart. First formula under kinetics is a first order, and the second is a second order. And then I can just determine the value of the rate constant. It's just the slope. And then I can do a little bit of math just using the formulas. So what I did is I graphed this, and I put the information in. You could do this in your calculator. I just did it in Excel. And I can see really quickly that the log of the concentration is not a good linear line. You can see that when I did the linear regression, that several of the dots are not points, data points are not on the line. I did do an R-square value, just although it's not really important, because it's pretty obvious which of the two is the straightest line. So here is the inverse of the concentration versus time, and much straighter. All the data points are on the line, and so very straight line. So very easily then, just looking at the graphs, I can answer my questions. I know it's a second order. So determining the rate law, I would just write that it is K NO2 raised to the second power is going to equal rate. So the integrated rate law, knowing a second order, is just that the NO2 inverse of the concentration is going to equal KT plus 1 over the concentration of NO2 initially. So that's going to be the answer to B. So this is A and this is B. And I'm going to use B in just a minute. And so C, very simple. All I have to do for C is I already know the unit because it's second order. So in second order, I take my molarity and I take away 1. So 2 minus 1 is 1. Make that negative. And then the time is given in seconds. Second is always to the negative 1 or over seconds. And so I know that's going to be my unit. So what's my value? So let's go take a look back at that graph. So if I look at the graph, I look at the inverse relationship, and here's my formula for the line, but it's hard to see. I'll rewrite it. Y is equal to 0.0002 plus 2.0125, which really worked out good because this is the initial, if this is the inverse of the initial concentration. So if I look at my formula and y equals mx plus b, there we go. There is my rate constant. So easy, so much easier than the differential rate law. So I know that my value here is going to be that 0.0002 molarity to the negative 1, seconds to the negative 1. So let's take another quick look because I want to make sure I did not lose a 0. So yep, 3 zeros and a 2. So then to answer this last question, very, very simple. I'm just going to take the information and plug and chug back into it. So what do I know? I'm looking for the NO2 concentration, not the inverse, but the NO2 concentration. But I'm going to plug it into this formula. I know K. And I'm going to show you how the units actually work out here. And I know time. It tells me my time. And I'm going to add the inverse of the initial concentration. So I'm going to pop up here. The initial concentration was 0.5. And that's going to be molarity on the bottom, or molarity to the -1. So if I work this out, if I calculate it out, I end up this answer right here comes out to be 4.8 molarity to the -1 because the seconds cancel, plus we all know that the inverse of 0.5 is 2. And so that comes out to be 2 to the -1. So I'm going to add that together. And so I'm going to have 6.8 molarity to the -1. That's going to equal my inverse of my concentration at that time. So then all I have to do is take the inverse of this. So if I inverse this, it gives me my answer. So I'm going to inverse. So I end up, if I take the inverse, is 0.147 molarity is going to be my concentration at that time. So it's just algebra, just plugging in. It's nice to use the units and making sure that that's going to be the correct answers.